Hello, today I'm solving the February-March 2020 variant for AS Chemistry 9701, variant 22, paper 2. The first question is on ionization energies across period 2. Construct an equation to represent the first ionization energy of oxygen, right? So we know that ionization energy is the energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. So oxygen has to be in the gaseous state, right? Also remember the state symbols cannot be in subscript. They need to be along the same line as the elements, alright? So this turns into a cation, right? And 1 mole of electrons is released. You had an alternate option. You could also write this loss of electrons. This also works. This is fine. State and explain the general trend in first ionization energies across period 2. Alright, so what happens? First ionization energies increase across period 2. This is not enough to get you 1 mark. You need to write something else. Due to increased nuclear attraction for valence or outer electrons. So this is really important. This gets you 1 mark. Now we're just going to explain why this attraction occurs, increased attraction occurs. This is due to an increase in nuclear charge, right? So nuclear charge increases, or you could also say positive nuclear charge increases, or there's alternate wording, the number of protons in the nucleus increases across the period, right? And the last mark is for saying that there is similar shielding of outer electrons, or you could say electrons are added to the same shell. Electrons are in the same shell, right? Electrons are added to the same shell. This also works, right? Or you could say that there is a slight increase in shielding. That is fine. Or same shielding works as well. Okay, same, similar, everything is fine. So why does A not follow the trend? As you can see, oxygen, it has an electron configuration of 1s2, 2s2. So what's the oxidation? What's the proton number of oxygen? It's 8, right? So 1s2, 2s2, 2p4. What about nitrogen? It's 1s2, 2s2, 2p3. So nitrogen has half filled orbitals, right? In the 2p orbital. What about oxygen? It has one 2p orbital which is, full, or it has 2 electrons in one 2p orbital or one p orbital. That's fine. If you just say p orbital, that's fine. But if you mess up, if you say something like 3p orbital, you're not going to get a mark, alright? So due to this, like we know that as we go across the period, right, proton number is supposed to increase, which results in increased attraction, right? This is their similar shielding. This is true for oxygen. Since proton number is more than nitrogen, it is 8 compared to 7, right? Nuclear charge increases, so attraction is supposed to increase, right? But on the other hand, this spin pair repulsion, this actually overweighs the increased attraction. So this is a new point that's been added to the mark schema, right? This wasn't there before. So we need to say that there is spin pair repulsion of electrons in 2p orbital. You could just say p orbital, 2p orbital of oxygen, right? This overweighs the increased nuclear charge, right? Ionization energy was supposed to increase, but the spin pair repulsion actually overweighs that factor. Okay, what's the electron configuration of E? It's in the third period, right? So it's going to be 1s2, 2s2, 2p6, right? Now, check this. There is a huge jump in ionization energy between the third and fourth one, right? As a result, it should be 3s2, 3p1, since it has 3 electrons in its valence shell, right? Due to this huge jump. That is what we need to say, right? The the greatest jump is between third and fourth ionization energies. This indicates that there are 3 electrons in the outer shell, right? I mean, if you say that it's in group 3 or in group 13, it might be okay, but it's just best to break it down to the examiner. Okay, sometimes it may be vague. What does being in group 3 mean? Right, you're supposed to break it down to the examiner in the simplest form, basically. Okay, define reducing agent. So guys, remember, a reducing agent is a species that donates electrons. Okay, so a reducing agent reduces somebody else and is oxidized itself in the process. So it donates electrons. Now always answer oxidizing and reducing agents in terms of electrons. Okay, a reducing agent donates electrons, and an oxidizing agent oxidizes somebody else but becomes reduced itself. So it's a species which accepts electrons, an oxidizing agent. And a reducing agent reduces somebody else, decreases the oxidation number of somebody else, right? You could also say gives up electrons, loses electrons, or a species that decreases the oxidation number of another. Okay, so Na2O with water, this is a basic oxide, it's going to form an alkali, right? So it's going to be NaOH. To balance it, we need 2. What does amphoteric mean? It reacts with both acids and bases. Or you could say it is a substance which shows both acidic and basic behavior. Both work. Okay? Shows both acidic and basic behavior. Okay? Al2O3 is purified from bauxite in several steps. The first step involves heating Al2O3 with an excess of NaOH. A colorless solution forms. Okay. So we're gonna heat Al2O3 and amphoteric oxide with a base. So we know that Al2O3 has the capacity to react with both acids and bases, so this will be a feasible reaction. This is a possibility. It's going to form NaAl OH4. This is a possibility. So what's the name of this compound? Sodium aluminate. This is hydrated sodium aluminate. Okay, this is sodium aluminate. It can also be anhydrous, but this is a possibility, right? To balance this, what do we need? We need 3 moles of water, right, to balance the oxygen. and 2 moles of this. Basically, you balance it like this. First, you give the 2 to balance aluminium. Then you need a 2 here, right, to balance the sodium, and to balance oxygen, you need a 3 here, right? So there were other options though. You could do this. Al2O3 plus 2NaOH is equal to 2NaAlO2 plus H2. This is also sodium aluminate, but this is the anhydrous form. Okay, this is the pure form, right? So these are the two options you should opt for. Any one of these two, okay? Al2O3 is used as a catalyst in the dehydration of alcohols. We do know that. So we want to show the effect of a catalyst on rate using a Boltzmann distribution. So suppose this is the activation energy for the uncatalyzed reaction. What happens when we use the catalyst? This is the EA, the activation energy with catalyst, right? So what happens? A greater proportion of molecules now have energy greater than the activation energy, right? So this you get 1 mark for this. Next, the second mark is like, for some reason in this mark scheme they did not say the catalyst increases the rate of reaction by lowering the activation energy. Thing is, that's going to be a repetitive point. You're already showing that on the diagram, right? So that point is already done with. You can also write it down, it's fine, they won't cut marks for it, but it's not required here. It's always better to write it down though, right? Remember that. The next point is a greater proportion, that's the best wording. A greater proportion, or you can say more molecules, right? A greater proportion of molecules have energy or with energy. So this is the key point, okay? It's greater than or equal to activation energy, right? Greater than or equal to. Now, the frequency of effective or successful collisions increases, okay? So P4O6 is a white solid which has a melting point 24, okay? It reacts with water to form H3PO3. Alright, so what does this tell us about the structure and bonding of P4O6? So what is the structure? The structure is simple, right? Why? Or you could say molecular. Why? Because it has a low melting point, okay? Now, what about the bonding? The bonding is covalent. Why? Because, so you cannot say it reacts with water, okay? You need to break it down. What is the reaction? Because it is hydrolyzed. You need to say that the reaction with water is actually hydrolysis. You could also say breakdown, right? But you cannot say reacts with water. If you just wrote simple covalent, okay, if you just wrote simple covalent, you would get 1 mark. Determine the oxidation number of phosphorus, H3PO3. So oxygen is always -2. -2 into 3 is -6. This is +3. So phosphorus has to be +3, right? When P4O6 is heated with oxygen, it forms P4O10. The enthalpy change of formation of P4O10 is -3012 kilojoules per mole. So let's make a Hess cycle. P4O6 plus O2, 2O2 is equal to P4O10. We know this. This is -1372. Now, for formation, remember, you need the basic elements below, right? You need the basic elements down below. Phosphorus exists as P4, by the way. You need oxygen, right? So the arrows should always be upwards in a Hess cycle with enthalpy of formation. So we are forming 1 mole of P4O10. and 1 mole of P4O6. So we don't actually know the enthalpy of formation of P4O6. This is unknown actually. So we can label it as HF, just HF, right? And this is known, this is minus 3012. So just follow the arrows. You either have a direct route from P4 plus O2 to P4O10, or you can take the detour using these two arrows, right? So we can say HF minus 1372 is actually equal to minus 3012. So if you solve this, you end up with minus 1640. That's all. Write an equation for the reaction of P4O10 with water. Okay, so it's an acidic oxide. P4O10 plus H2O is equal to, we know that we're going to form phosphoric acid, right? So it's going to be H3PO4. If we want to balance this, we need a 4 here, and we need 6 moles of water. HPO3 was also accepted, but just go for this. This is much better. Construct an equation to show how NO2 is regenerated in the catalytic oxidation of SO2. So we know that NO2 is the catalyst, right? So NO can react with oxygen again. NO can react with oxygen again to form NO2, right? So this is the new addition to the syllabus. NO2 can also react with unburned hydrocarbons to form photochemical smog. State the product of this reaction that contributes to photochemical smog. The reaction between nitrogen oxides and unburned hydrocarbons, right? It's PAN, PAN, or peroxyacetyl nitrate. New addition to the 2022 syllabus. This was interesting. So the equilibrium reaction in equation 1, this one, SO2 plus N2, they're saying that it is exothermic. Okay, suggest how the position of this equilibrium differs at a height of 20. This is our subject, compared with a height of 50 kilometers. So check this out. At 20, the temperature is around minus 60, and at 50, the temperature is around 0. So basically at 50 degrees Celsius, the temperature is higher, and at 20 kilometers, the temperature is lower at minus 60. All right. So how are we going to answer this? Think about it. At 20 km, right, the temperature is minus 60 degrees Celsius, and at 50 km, it's around 0 degrees Celsius. Okay. And we know that the forward reaction is exothermic. So a lower temperature actually favors the forward reaction, right? So the equilibrium should lie to the right. That's the logic. The position of the equilibrium actually moves or lies farther to the right at 20 kilometers. Okay, why? This is because the forward reaction is exothermic. So we know the Le Chatelier's principle states that we're going to oppose the change. And we need to mention something else. The forward reaction is exothermic, and we need to mention that. And temperature is colder at 20 degrees Celsius. All right, you need to mention this, or you can just say that there is due to the decrease in temperature, the equilibrium moves to the right. Right. So it's basically the position of the equilibrium lies further to the right at 20 degrees Celsius compared to 50. Why? Because at 20 the temperature is lower, or there is a decrease in temperature, and the forward reaction is exothermic. That's what you need to write. Okay. So question 3 is on halogens. So this is the new mark scheme. This is what we need to follow. So just remember that halogens are oxidizing agents, right? Halogens are oxidizing agents. So basically, how do oxidizing agents act? They are species that gain electrons. So think about this. You have chlorine, bromine, and iodine. Who's the better oxidizing agent? It's chlorine, right? Why? Chlorine can easily oxidize hydrogen, right? Why? Because it's smaller, it has a smaller atomic radius, and it has higher electronegativity, right? So it is more likely to attract or take the electron from hydrogen. So as we go down the group, what happens? Size increases, electronegativity decreases, the they are less likely to attract the electron, right? And they become weaker oxidizing agents. So we know that down the group shielding does increase, right? Because electrons are added to new shells. But the greater nuclear charge actually outweighs the or overweighs the increased shielding. What does this mean? This is a point in the mark scheme. The greater nuclear charge overweighs the increased shielding. All right. What does this actually refer to? So basically, we want the halogen to accept electrons easily, right? As an oxidizing agent. However, as we go down the group, proton number is increasing, right? So there's increased attraction for the valence electrons. So this is actually this greater nuclear charge, right? It actually overweighs the increased shielding down the group as the atom becomes larger. So what is the implication of this? Why does reactivity? So the first one, I'm going to explain again. Reactivity decreases down the group, or the reaction becomes less vigorous down the group. You guys know that hydrogen reacts with fluorine in cool conditions, dark conditions. Hydrogen reacts with chlorine with UV light or high temperature. For bromine, it requires higher temperature, and for iodine, it requires much more higher temperature, 450 degrees Celsius, provided by a hot glass rod. It provides the activation energy. So it becomes less vigorous down the group, right? Less explosive. So what is the main reason? It's basically due to the strength decreasing, strength as an oxidizing agent to decreasing. You need to think of halogens. What are they? They are oxidizing agents and they accept electrons. Since their ability to accept electrons decreases down the group, right? That's why they become weaker, right? And the reactivity also decreases the enthalpy. So to get the second mark, you had around 6 points. You had to write any two from them. These are the points: electronegativity decreases down the group of halogens. We're talking about halogens. Halogens are less attractive to electron addition. They become weaker oxidizing agents, or you could word it this way: oxidizing power decreases down the group. There is another point, by the way: atoms become larger. The bond dissociation energy of halogen halogen XX halogen halogen becomes smaller down the group. Although they did tell us to ignore the hydrogen halogen bond here, though. All right. HCl is a product of several different reactions. Write an equation for reaction 1. SiCl4 plus H2O is equal to SiO2 plus 4HCl. So we need a 2 here. So salts, right? Sodium halides, they react with concentrated H2SO4. However, you guys know that sodium bromide and sodium iodide undergo multiple reactions. Why is that? Because they're stronger reducing agents. So concentrated H2SO4, the oxidizing agent, it is actually strong enough to oxidize them. But since chlorine is a stronger oxidizing agent than H2SO4, H2SO4 can't really oxidize chloride, okay? So what actually occurs? No redox reaction occurs, only an acid-base reaction occurs. Remember, it is not a neutralization reaction since water is not formed. Check this out. Water is not formed, okay? So NaHSO4 plus HCl, water is not formed. So what happens here? The acid-base reaction will occur in the first step, followed by redox. So you needed 2 to get 1 mark and 3 to score all 2 marks, okay? What about the explanation? I just told you guys H2SO4 is strong enough to oxidize NaBr or HBr, you know, the product of the reaction, or just bromide, Br minus. When heated with the Bunsen burner, HCl does not decompose, whereas Hi decomposes. Why is that? This is mainly because HCl bond is stronger than Hi. Or you could say the bond dissociation energy decreases down the group. This is also fine. The hydrogen halides dissolve in water to form strong Bronsted-Lowry acids. So what is a Bronsted-Lowry acid? Mainly, it is a proton donor. Bronsted-Lowry acid is a proton or H plus donor. Now we need to say what strong means. So it's a proton donor which fully or completely dissociates, in water or in aqueous solution. This is it mainly. Now this is also a new addition to the syllabus. So don't misinterpret it. NaOH is being added to the acid. So the initial pH is going to be acidic. And we are adding an alkali to the acid, right? So pH is going to increase over time. So think about it. HBr and NaOH and HBr and NH3. All 3 of these are actually monobasic acids and monoacidic bases. So they will react in a 1:1 molar ratio, right? So we are adding 0.1 mole per dm cube of NaOH to 0.1 mole per dm cube of HBr and 25 cm cube. So think about it. Since they have the same concentration and the same molar ratio, we are going to need 25 cm cube of NaOH and 25 cm cube of NH3 to neutralize it. So our vertical section is going to be at 25. This was our first point, okay? The vertical section is at 25. Now the initial pH. So HBr, right? The initial pH, think about it, HBr is a strong acid. Strong acids typically have a pH of 1. So the marking point was at less than or equal to 2. It had to be less than or equal to 2. So it needed a pH of 1 maybe. Both of them start at 1. And since it's a strong acid, right, we know that the vertical section is going to be a bit taller comparatively. It's going to be a bit taller. For a weak acid, it typically starts at 8, 7 or 8. But for a strong acid, it starts at 11, 10, 11, 12 maybe, okay? So it's going to go, it's going to start at, sorry, for a weak acid, it's at 7 or 6. For a strong acid, it's like at 4, 3 or 4, okay? So it's going to be like this. Then we get the vertical section. Since NaOH is a strong base, it's going to end at 13ish. At around 13. When all of it has been added, it's going to end at 13. So 7 minus 3, 4. We're going to add 4. So add 11. Yeah. The graph is going to be like this. This is typical for as strong as a strong base. What did I do? Check this. 7 plus minus 4. Those are the points where the vertical section ends. Right? 7 plus minus 4. So it's actually 3, 3 to 3 to 11. The length of the vertical section. And for a weak acid and weak base, it's typically 7 plus minus 1 usually. Alright? So 6 to 8 typically. So since it's a strong acid, it's still gonna start at 3ish, like this. You draw the vertical section, but now it's gonna change. Basically, the last pH, the final pH, cannot be 13, right? It has to be less than 12. It has to be less than 12. At maybe 11 or something, 11 or 10, right? And I also taught you something that the vertical section will end at 8. The vertical section will end at 8, right? And we can't have it crossing 12. It cannot cross 12. Okay, you need to remember that it cannot cross 12. And there will be a kink in the drawing due to the buffer action of the weak acid. You can learn about this in A2. So like typically we would have drawn it like this, right? But we can't. Since it has a buffering action, the curve should be like this. This is the best diagram that you could draw possibly. All right. So let's make it end at 11ish. Let's make it end at 11. So the diagram is going to be like this. Okay. This is the perfect sigmoid shape. Okay. Ask me if you have any questions. So now we finally have organic. Right. So HBr reacts with propene to form 2 bromoalkanes. Either 1 bromopropane or this is 1 bromopropane or check this. 2 bromopropane. 1 or 2 bromopropane. So we want to show the major product. We know that 2 bromopropane is going to be the major product, right? So we need that. Let's see. What are the marking points? We first give the dipole, del plus and del minus. Then we show the curly arrows, right? Always remember it's going to be a curly arrow from the electron rich region to the electron deficient region, like this. So the next step is going to be, remember, the carbocation is going to be at the carbon which has more alkyl groups. So compare this carbon, it has none, right? What about this one? It has one alkyl group, so the carbocation is going to be there, right? And hydrogen is basically reacted with that carbon and the double bond is gone. That carbon now has 4 bonds, but the carbon in the middle, right? The carbon in the middle, it has 3 bonds, right? It still has 3 bonds and it turned into a carbocation. So who's going to attack this carbocation? The bromide anion that we formed in the first step, right? So we draw another curly arrow and we end up with this CH3 C CH3H Br, right? This is 2 bromopropane. So why are they not produced in equal amounts? Why is this the major product, right? Mainly because you need to make a comparison. The 2-degree carbocation, right, formed here. The 2-degree carbocation is more stable, keyword is more stable than the 1-degree carbocation. Why? Now we are going to answer why. Due to the positive inductive effect, or the electron donating effect, right, of 2 methyl groups, or you could say 2 alkyl groups. That's fine. So we know that halogenoalkanes react with NaOH in 2 ways under 2 conditions. One, if NaOH is dissolved in water, and 2, if NaOH is dissolved in ethanol, alcoholic conditions, alcoholic solvent, right? So let's see what happens. If it's water, nucleophilic substitution reaction takes place, or hydrolysis, we call it hydrolysis. So Br is replaced with OH. So this is CH3, CH2, CH2OH. This is propan-1-ol. You could write that down if you want. Don't write both though. So check this: CH3, CH2, CH2Br plus NaOH is equal to CH3, CH2, CH2OH plus NaBr. So this is our inorganic product, right? What about the next one? In ethanol, an elimination reaction actually takes place, right? So CH3, CH2, CH2Br. This reacts with NaOH to form, right? CH3, CH2, or CH3, CHCH2. So what did we lose from the left hand side? We lost one hydrogen and one bromide. Okay, one hydrogen and one bromide. So where do they go actually? Remember that NaOH has two parts, Na and OH, and we lost one molecule of HBr, right? So where do these H and Br go actually? So the H combines with OH to form H2O, and the Br combines with Na to form NaBr, right? So it's going to be NaBr plus H2O, and the product is going to be CH3CH2, right? Elimination. Next, we have J and K, which are found in plant oils. Observation with J, 2,4-DNPH. Since there's an aldehyde, we're going to see a red, orange, yellow precipitate, right? An orange precipitate, PPT, or solid. You could write the full form, by the way. Toluenes, right? Since it has an aldehyde, we're going to see a silver mirror, okay? Or a silver precipitate, that's fine. Sodium metal, right? It's going to react due to the presence of alcohol and carbox alcohol group, right? So we're going to see effervescence or bubbling. Effervescence or bubbling or fizzing. Okay. Now, J has two optic isomers. Okay. So how do you draw these diagrams? This is how you do it. First, draw the center carbon. Now, choose what you want. Let's make OH go on top. We can do that. This doesn't have to be laterally inverted, the one on the top, okay? Now, CHO is on the right. So, suppose if you draw CHO like this, you need to ensure that you draw CHO like this, okay? Next, if you show CH3 here like this, CH3, then you can't draw CH3 here. That would be wrong. You won't get 1 mark. You need to draw CH3 like this. It needs to be a mirror image basically, okay? This is what I want to teach you. So it's going to be CH3. What about the last one? It's COCH3. That's a methyl ketone group, right? COCH3. So COCH3. So it's going to be COCH3. Remember, the carbon has to be bonded to the center one, alright? Now, next part, K is used to make the addition polymer for perspex. Okay, identify L. What happened here? Esterification, right? We added a 1 carbon alcohol to the carboxy acid group. So what is the 1 carbon alcohol? It's none other than methanol, CH3OH. What are the conditions for esterification? A few drops of, H2SO4. A few drops of concentrated H2SO4 plus heat under reflux. Remember, reflux is the keyword here. Draw 1 repeat unit of perspex. Okay. Here we go. This is it. Dangling bonds, right? Use information to suggest how the infrared spectrum of M and perspex would differ. So perspex doesn't have an alkene, but M does, right? So perspex would actually be missing this absorption in this range. So we can say that perspex, trademark registered, right? would not have absorption, not have an absorption at 1500 to 1680 per centimeter, since it does not have the alkene or the C double bond C, right? Next, K can be made from propanone in 3-step synthesis as shown. Okay, so what's the first step? It's actually nucleophilic addition, right? So they just wrote addition for some reason in the mark scheme, but you could write nucleophilic addition, you'll get marks. They said ignore those words. They aren't marking you for those, okay? And what reagent do we need? We need KCN and HCN, okay? HCN is the reagent and KCN is the catalyst. Next, reaction 2 is acidic hydrolysis. They just wanted hydrolysis. And for this, we need a dilute acid. You could write dilute acid or H plus aqueous or any other acid, HCl aqueous, H2SO4 aqueous, that's fine. Okay, but you need to mention aqueous or dilute. It can't be concentrated. So Al2O3, what does it do? The next step, we know that Al2O3 is a dehydrating agent, right? So this is mainly elimination or dehydration. Both work. So if you guys have any questions, you can ask me.